the equilibrium constant. So this is a way to quantify the concentrations of the reactants and products at equilibrium. And this type of expression here illustrates the law of mass action. I'm not going to quiz you on that, but if if that term comes up, this is what they're referring to. The equilibrium constant is equal to the concentrations of the products raised to an exponent that's equal to their coefficient in the balanced chemical equation. So we have the products in the numerator divided by the reactants. I remember as a student having a hard time remembering which one goes on top, the products or the reactants. And what helped me to remember is, delta is always final minus initial. So this, what's the final one here? Well, it's the products, right? So it's final divided by initial. So if that helps you, great. If it doesn't, come up with something else. Feel free to share it with me. When we put a formula in brackets, we mean the molar concentration of that substance. So we're not going to be putting units in here. The brackets tell us it's moles per liter. Now this, I just want to point out, so this is a non-italicized capital K, and this is an italicized capital K. This one's just kind of slanty, right? Unitalicized, that's the abbreviation for the unit of temperature known as Kelvin. And italicized is a variable, or it's a variable that can have different values depending on when you're using it. So that's why these lowercase letters are italicized, because they represent numbers. So in the slides, in the text, we try to be very consistent. This is an italicized K. But I just want you to be aware that you're going to see some temperatures in kelvins as well. And so just be aware that there's two capital Ks out there, and you kind of have to look at the context to see which one you're dealing with, okay? Okay, so according to the law of mass action, that pattern we just looked at, what is the correct expression for the equilibrium constant for this reaction? 2A plus B is in equilibrium with 3C. It's letter D. So we've got C cubed divided by A squared times B. So that's the correct expression. So when we go to write something like this, we're like the equilibrium constant, and we look at the concentrations of the products raised to the coefficient, divided by the concentrations of the reactants raised to their coefficients. And chemists often just don't write the number 1. So there's an implied number 1 here. There's an implied number 1 as the exponent, but we don't normally write that. Any questions? This should remind you of writing a rate law for an elementary step. In an elementary step, we can use the coefficient as the exponent and be safe, but we can't do that if it's just an overall chemical reaction. So let's look at that in terms of an actual chemical equation. So here we have an actual chemical equation. So the equilibrium constant is the concentration of the first product raised to the 4th power because the coefficient is 4, times the concentration of O2, implied 1, raised to the power of an implied 1. And then we divide by the concentration of the products. Here's the concentration of N2O5, and it's squared. You see the pattern there? Compared to some of the things we've looked at, this should be a nice friendly pattern. It's really nice and consistent. Okay, so write the equilibrium or express the equilibrium constant for the combustion of propane as shown by the balanced chemical equation. So I'll give you a minute and you try doing that. Okay, so K equals, what goes on the numerator there? CO2 in brackets representing molarity. And what's the exponent? 3. And then that is times the H2O concentration in brackets. And the exponent is 4. And then we're dividing by the reactants. C3H8 doesn't have a coefficient, has a coefficient of 1. And so the exponent is also 1. And then we have oxygen to the 5th power. Any questions? So the significance of the equilibrium constant, specifically its size. When K is a large number, much bigger than 1, what that means is that the numerator is big and the denominator is small. That means the product concentrations are large and the reactant concentrations are small. So a large equilibrium constant says that the reaction is going to favor the products. When we look at what's present at equilibrium, we're going to see, well, it's mostly products. There's some reactants present, but not very many. And when we're talking about sizes of numbers, these can be really big. So here's an equilibrium constant, 1.9 times 10 to the 19. Super, super big. If K is very small, like 4.1 times 10 to the minus 31, that means that the numerator concentrations are very small and the denominator is big. So a small rate constant will favor the reactants. So looking at this at equilibrium, we see that there's mostly reactants here and only a little bit of product. Now, when you have a number that is this small, and you look at your beaker of solution, there may be only a handful of product molecules out of gajillions, right? But it's not zero. There's almost always something left, because even if there's one particle, it's not complete. Important to remember, the equilibrium constant says nothing about how fast the reaction gets to equilibrium. It could get to equilibrium within seconds, or it could take years, anywhere in between. Any questions? Pardon me? What determines how long it takes? Well, that's a great question. So that's more in the kinetics, right? So the concentrations would affect it, the types of collisions necessary, the temperature, the activation energy, those sorts of things would all have an effect on it. Yeah, good question. So if K is very small, the reverse reaction is favored. If K is very big, the forward reaction is favored. If K is close to 1, then we have that situation where it's about halfway. And the concentrations of reactants and products may be similar to each other. So I don't find it useful to try to memorize something like this. I find it more helpful to think about Okay, just, generic equilibrium constant. If this is a small number, what does that mean about the relative sizes of those? Well, it means what's on top has to be small and what's on bottom has to be big. Okay, so that means the reactant concentrations are bigger. And yeah, that may take, 5 or 10 seconds to think through, but you're not going to get it mixed up. So let's look at this reaction, A going to B. And again, they've used just colors. So we've got A is red and B is black, and we've got an equilibrium mixtures at 3 different temperatures. Temperature can affect the equilibrium constant. At which of these temperatures is the equilibrium constant K the largest? Does a large K favor the products or the reactants? Favors the products. So which of these has the most black circles? It's C. Any questions about that? You see how that works? We do a lot of calculations with these things. We need to be able to do that. We also need to understand the concept. The equilibrium constant for the reaction A goes to B is 10. Reaction mixture initially contains A is equal to 1.1 and B is equal to 0, which statement is true at equilibrium. This is a conceptual connection problem. We shouldn't need a calculator. Can we eliminate any of the choices? What about C? The reaction mixture contains equal concentrations of A and B. Is that what equilibrium means? No. Could that ever happen? Yes, it could happen. Really rare. Really, really rare. Okay, so we've got one of these. Here we have, in the reaction mixture at equilibrium, we've got more reactants than products. And here we have more products than reactants. So which of those combinations could give us K equals 10? It needs to be B. Because K is equal to the concentration of B divided by the concentration of A. You could certainly calculate this and find it out, but because it's multiple choice and we just know the directions, you could also just choose this without using a calculator. Any questions? Okay, so relationships between K and the chemical reaction. If you dig into your brains back to Chem 1A, we talked about heats of reaction, and we talked about Hess's law, and we did some things where we added reactions together, and sometimes we reversed them, and we multiplied them by coefficients. Do you remember doing that? I didn't ask, do you remember how to do that? Do you remember that we did that? Okay, that's good enough. So we had rules for adding those equations and combining delta H. We have similar rules for adding equations and combining equilibrium constants. But the way I think of this, we added or multiplied in with the delta H. Here, instead of multiplying, we're going to raise to a power. So if we reverse the equation, so here's our chemical equation, if we write it backwards, what we did with delta H is we multiplied by -1 to reverse it, right? Because it was going in the opposite direction. Here, instead of multiplying by -1, we're raising to the -1 power. We are inverting the equilibrium constant. So let's see how that works here. So this is the forward reaction, and so we're going to have C cubed over A times B squared. And for the reverse reaction, we're going to have A times B squared divided by C cubed. So K reverse equals K forward to the negative 1 power, which is 1 over K forward. So there's a reciprocal relationship. Instead of changing the sign, you reciprocate them, you invert them, upside down them, if that works better. You see how this one is just upside down of this one. When we raise something to a negative power, that inverts it, puts it in the denominator. Any questions about that one? If we multiply the coefficients in the equation by a factor, so we did that with Hess's law, we have to multiply everything by 2. And then we would multiply delta H by 2. Well, here, instead of multiplying by 2, we're going to raise to the power of 2. So here we have A plus 2B goes to 3C. And here we have the same equation, but multiplied by some integer n. So maybe it's 2 or 3 or whatever. So we can write the equilibrium constant expressions for these. C cubed over A times B squared. So in this one, it's still a concentration of C, but we raise it to the exponent equal to its coefficient. Well, now its coefficient is 3n, 3 times n. And we're going to divide by these guys. We're going to divide by A, but it's no longer to the first power, it's to the n power. And B is to the 2n power. So let's do that without variables, okay? So let's say we have 2A plus 4B is in equilibrium with 6C. How did I get this chemical equation from that one? I multiplied by 2, right? We can write the equilibrium expression for this. It's C to the 6th divided by A squared divided by B to the 4th power. That is the same as, C cubed over A times B squared, the whole thing squared. We could write this one similarly. We take the whole thing and raise it to the power that we multiplied the equation by. Any questions? One of the things I like about math and about a lot of chemistry is that there are patterns. And if you learn the pattern, you can do lots and lots of different things. Yeah, so here this is called K prime because this will not be the same number as this K because the equation has changed. So K prime is equal to K to the n power, another way to express that. Okay, if we add two or more chemical equations together to get an overall equation, what we did with delta H is we added the delta H's. You add the equations, you add the delta H's. With equilibrium constants, instead of adding the equilibrium constants, you multiply them. So let's see what happens here. If I add these two equations, before I start writing stuff down, I'm going to see if there's any intermediates. So here B is being formed and then it gets destroyed. So those are not going to show up in the overall equation. So the overall equation is A goes to 3C. So let's call this K3, and let's write the equilibrium constant from this equation. Well, it's going to be C cubed divided by A, right? So what this rule says is that K1 times K2 is going to equal K3. If I add the equations, then the equilibrium constant will equal the original ones multiplied. So let's see if that's true. So K1 was B squared over A, and that's times C cubed over B squared. And let's see, does that equal C cubed over A? Well, the B squareds are going to cancel out. So yeah, they're equal. I'm showing you this so you have an easier time believing me when I say that's what you need to do. When we have it simple like this and we do this, we can see, oh yeah, that's how it works. We're not going to do stuff like this if we're actually adding equations together and trying to get the equilibrium constant. We're going to know the equilibrium constant for each of our things, and we're just going to multiply, because that's what the rule says. This is why the rule is the rule. Any questions? Okay, let's look at this one. So the reaction A going to 2B has an equilibrium constant of K equals 0.010. What's the equilibrium constant for the reaction B going to 1/2 A? What we're looking for is, how was the chemical equation changed? What happened to it? It got reversed, right? So the equation was reversed. And what else? Here the coefficient was 1, and here the coefficient is 1/2. So it got multiplied by 1/2. You could say divided by 2, but multiplied by 1/2 works better for how the rules are worded. So our initial K, what do we need to do with it when it's reversed? We need it to the -1. And then if we multiply by 1/2, what do we do? We have the exponent is now going to be -1/2. So let's look at it this way. This is 1 over K. And so here we've got 1 over K raised to the 1/2 power. I think it's easier to see that way. This is the inverting for the switching of the direction of the reaction. And then we multiplied by 1/2, so we raise this to the power of 1/2. So this is 0.01. 1 over 0.01. Oops. What does that equal? 100. So that's 100, and to the half power. And you're more familiar with that as this. Raising something to the half power is the square root of that number. If you don't remember that, you can use your calculator, raise it to the half power, and you'll get the correct answer. So what's our answer? 10. Any questions? Okay, so that was kind of a, more of a baby practice question. So this one's got a real chemical equation with a real rate constant. Consider the following chemical equation and equilibrium constant at 25 degrees Celsius. Calculate the equilibrium constant for the following reaction at 25 degrees Celsius. Why are they specifying the temperature? Do we need to use that in the calculation? No. The temperature affects rates of reaction, right? It's going to affect the rate of the forward and the reverse reaction, and maybe not in the same way. So the equilibrium constant will probably change at a different temperature. So all they're doing here is they're saying, we're at the same temperature, you don't have to worry about temperature. So what we need to figure out is, how do we get this chemical equation to look like that chemical equation? Well, first of all, it's reversed, right? Because here, these are products, and here they're reactants. So let's reverse that. CO2 plus CF4 in equilibrium with 2 COF2. So the equilibrium constant for this one then is 1 over K. You reverse the reaction, you invert the K, raised to the negative 1 power. Everybody okay with that? And then all of these coefficients are twice as big. So everything was multiplied by 2. So what do I do to my K? I raise it to the power that I multiplied those by. So let's apply these operations to our rate constant there. I'm sorry, equilibrium constant. Our rate constant's on the brain. So we could do 1 divided by 2.2 times 10 to the 6, and then square that. And since they gave us 2 sig figs, it's probably 2 sig figs, 2.1 times 10 to the minus 13. So I put this value in where the K is. 1 over this number and squared it. Any questions? That make sense? The individual pieces aren't hard. The problem is remembering them, right? And so if you can find some explanation in your head, some reasoning, it really helps. So for me, I think of the delta H's. You would change the sign, you would multiply. Here, it's similar functions, but they're ramped up a notch. Instead of multiplying, we're raising to a power. So instead of multiplying by -1, we're raising to the -1 power. Instead of multiplying by 2, we're raising to the second power. Predict the equilibrium constant for the first reaction given the equilibrium constants for the second and third reactions. This is even more like the Hess's law problems we did in Chem 1A. So we have two chemical equations here, and we have to figure out how can we manipulate these and add them together to get that one up there. There's C's and O's and H's all over the place and some numbers, and it's really easy to mistake CO and CO2 and get things mixed up. So I like to use colors and highlight this. You could, so if you've got colored pencils or something, here's your excuse to buy highlighters. You can do that. The other thing is you could make a code and say, well, I'm going to call this A, and I'm going to call that B, and I'm going to call that C and D, and just do it with simple letters that way. But I'm not going to do that. So I'm going to highlight the CO2s in yellow, and hydrogen is going to be red, just because that was what I thought of. Water's going to be blue, because water is blue. And methanol's going to be purple. And then make the CO orange. Makes it easier to match things up. So I'm going to look at what I'm trying to make, and I'm going to look at the pieces I've been given, and I'm just going to start with the first reactant. The first reactant is CO2, so I need to use something that's going to have CO2 as a reactant. Well, this is the only one that has CO2 in it, but it's in the product, so I need to reverse it, right? So I'm going to try to keep my arrows lined up here. So this is going to be CO2 plus H2 going to CO plus H2O. So yellow and red were products, now yellow and red are reactants, orange and blue were reactants, and now they're products. Okay, so let's maybe call this K4. K4 we're going to get from K2. What do we do to it? Raise it to the -1 power or invert it, right? So that's going to be 1.0 times 10 to the -5. Next thing I need 3 hydrogens. Well, I have 1 hydrogen here. Can I just multiply this by 3? No, because then I have to multiply the CO2 by 3 also, and that isn't 3. So this other equation has hydrogens in it, so I'm going to stick that in there. If they give you 2 equations, you're going to need to use both of them. So this one, CO plus 2H2, CH3OH. We're going to have to add these together. So if I add one H2 to two H2s, I'm going to get the three H2s I need. Okay? And so I just need to add these together. What I did here is I was focusing on the reactants, and I'm looking at how can I get the reactants to come out correctly. If you don't make any, mistakes in copying stuff down, the products will take care of themselves. So I've got the reactants. Okay, so I'm going to add, did I do anything to that K? No. So K, it's still K3, 1.4 times 10 to the 7. So I'm going to add these together. The CO gets formed there and destroyed here. CO2 gas plus 3H2O, 3H2. H2O no would be something else. And CH3OH and H2O gas. I manipulated these two chemical equations so that I could add them together and get the one that I want. So K for this then is going to be these two guys multiplied. So K1 is going to equal K4 times K3. So it equals 1.0 times 10 to the minus 5 times 1.4 times 10 to the 7, which will be 1.4 times 10 to the 2. Which could also be written as 140. Make sure your calculator is cooperating with you. $140. And here we are at 16.4.